It is possible to combine relations using set operations because simply relations are sets themselves. So we can use union, we can use intersection, set difference, symmetric difference, etc. To combine relations. But of course, the domains and the sets should be suitable for this. If R1 and R2 are two relations, both from A to B. If they are from different sets to different sets, this may not be possible. But if they are from both from set A to set B, and then we can define the union of two relations. It's simply a union because the two relations are sets themselves, sets of ordered pairs. So you just take the union, and the zero one matrix becomes an element-wise OR operation. And you have the intersection of two relations, and the zero one matrix is element-wise AND of the two matrices. And in a similar fashion, you can define difference R1 difference R2, or R2 difference R1, or the symmetric difference, etc. The next concept we are going to talk about is composing relations, the composite relation. This is quite important. And here, be careful about the setting. Relation R1 from A to B and relation R2 from B to C. So it's like R1 from A to B and R2 from B to C. Okay, so these are important. The order of the sets is important for us to be able to define the composite relation. Now, the composite relation R2 composed with R1, and the order here is not a typo. R2 is written first. The composite of R1 and R2 is defined as the relation given here for all x in A, y in B, z in C, if x and y are related through R1, and at the same time y and z are related through relation R2, then xc should be related through the composite relation. Okay, so x here, y here, they are related through R1, and this y is related to z through R2, then x and z in sets A and C respectively should be related through the composite relation. Again, be careful about the order. So this is like composing functions. When you remember composing functions, if you compose function f1 with f2, you write this, and similarly this was f2 applied to f1 applied to x. So this is the same idea here. R1 composed with R2. When you have something like this, you just put R1 here, R2 here. Be careful about the order. And obviously here, assuming that the cardinalities of sets A, B, C are M, N, and P, the cardinality of A is M, the cardinality of B is P, and the cardinality of C is N. Therefore, the 0, 1 matrix of relation 1 is an M by P matrix. The matrix of relation 2 is P by N, and the matrix of the composite relation in this case is going to be an M by N matrix because it will be defined from set A to set C. Okay, now let's look at how to construct the matrix of the composite relation. For the element ij, the row I, column j element of this 0, 1 matrix of the composite relation, for that element to be 1, there needs to be at least one k such that I and k are related to each other through R1, and at the same time k and j should be related through R2. Okay, there needs to be at least one such common element. Therefore, if that common element is 1, okay, M1 I1 and M2 1j, or if it is not 1, maybe it is 2, element 2, okay, in set B, I in A is related to 2 in B, and 2 in B is related to J in C. Or it's not the 2, it's 3, or it's 4, or it's maybe the final element, number P. I is related to P, and P is related to J. If either one of these is satisfied, then this will be 1, otherwise it will be 0. So in short, I can write this as a big OR with M1 IK and M2 KJ. Now this we denote as this expression, and we call this the Boolean product. Boolean product of two 0, 1 matrices, two Boolean matrices. All components are 0 or 1, and this is how we define the Boolean product of two matrices. This is very similar to ordinary matrix multiplication, except instead of addition, you use OR. Instead of multiplication, you use and that we call a Boolean product. And the composite relation has the 0, 1 matrix you obtain when you take the Boolean product of the 0, 1 matrices of the relations. Okay, and the composite relation on itself of a relation R can be defined recursively. Now here we defined the composite relation of two relations, R1 and R2. And what if R1 and R2 are the same relation? Okay, a relation R on set A, so from A to A. Let's compose this relation with itself. And we define this recursively. In the basis case, R to the power 1 is R itself. And in the inductive step, or the recursive step, we define R to the power n plus 1, the composite relation, as the composite relation of R and R to the power n. Okay, so this is simply R to the power R1 is R square is R composed with itself, R cubed is R composed with itself, then composed again with itself, etc. You get the idea. Okay, in this case, of course, the 0, 1 matrix can also be stated in a recursive way, and m to the power 1 through a Boolean product is equal to itself, and m to the power n plus 1 is equal to m to the power n Boolean product with matrix M. Now, we are going to use this when we talk about transitivity of a relation. Relation R on set A is transitive if and only if for all powers n, R to the power n is a subset of the relation R. Okay, now we have defined the composite relation R to the power n recursively, and this is going to enable us to detect the transitivity of a relation. And we are going to prove this, well, since we have the expression if and only if, this is a biconditional. Therefore, I have to prove this both ways. So the first part is if you have this, then this implies R is transitive. Let's prove this. For n, x, y, z in A, let's assume x is related to y and y is related to z. Okay, now, but based on the definition of the composite relation, x is related to y and y is related to z, then when I compose R with itself, then the pair x to z here should be in the composite relation. Okay, this means xz is an element of R square. Okay, now I know that for any n, R square is a subset of R. Therefore, R square should be a subset of R, which means any element in R square must be an element in R, which means xz is in R, which means x is related to z in R. Therefore, when you have these, you also have x related to z, which is by definition yields the transitivity of R. So that's one implication proven. We also need to show it the other way. When R is transitive, this subset relation is satisfied for any n, and we are going to prove this using induction. And our basis step is trivially true because when n equals 1, R is a subset of itself. It's true. In the inductive step, I need to show this implication. Okay, so this is true for n equals k, and this should imply the same statement for k plus 1. So we have implications inside implications, and this is going to be my inductive hypothesis, and I'm going to assume this. And from this, I would like to reach to this. Now, again, take x, y, z elements in A, and let's say x is related to y through the relation R to k, and y is related to z through R. Okay, and R here is transitive. Now, xy is in relation R to power k, and yz is in R, and therefore these together entails, by definition of composite relation, xz is in R to k plus 1. Okay. Now, by our inductive hypothesis, this implies, since Rk is a subset of R, this implies xy is also an element of R, because R to the k is a subset of R. And therefore, since R is transitive, this together with this entails xz is also in R, because R is transitive. Okay. Now, since I have this and this, you see, this x and z being related through R to the power k plus 1 implies x and z being related through R, which is by definition, whenever this is true, this is true. This means R to the power k plus 1 is a subset of R. Okay, so whatever k is, this is going to be true. Whenever this is satisfied, R to the power k plus 1 will also be a subset of R, because whenever you have this pair in this set, you will also have that in this set, which is by definition shows that R to k plus 1 is a subset of R. Therefore, the inductive step is also proven. And therefore, you see, coming back to this statement at the beginning, we have the test for transitivity. A relation R on set A is transitive if and only if for all n, when it is composed with itself n times, for all n value, the result should be a subset of relation R.